the workshop. The first talk today is by Noah Stephens-Davidowitz, who will tell us about the average case hardness of K-sum. Please, Noah.
Okay, great. So yeah, hi, I'm Noah. And yeah, I'll be talking about the hardness of average case K-sum, which is joint work with Zvika and Vinod, my two lovely co-authors. Okay, so let me remind you or tell you for the first time what the K-sum problem is. It's extremely natural and seems very fundamental in the study of fine-grained hardness. So the input to the K-sum problem, it's the computational problem. It has some input. There are a bunch of numbers in ZQ. So a bunch of group elements in the group ZQ. And you should think of the parameter regime where sort of M and Q are going to infinity. And K is maybe a large constant or maybe going to infinity, but rather slowly relative to M and Q. And the goal is simply to find a K-tuple of your elements that sum to 0 modulo Q. So you might have seen variants of this problem in different groups, like over the integers or over like ZQ to the N or whatever. It doesn't really matter much. Sort of everything I'm going to say works over your favorite abelian group if you have a favorite abelian group. But it's going to be easiest for me in this talk to discuss ZQ. And so just remember the parameter setting that I'm in. I think of K as like a constant or maybe something that's going to infinity very slowly. And Q and M are sort of the parameters that are asymptotic that are really going to infinity. Okay, so of course this is some computational problem, and we're all computer scientists here. So the question that we ask is, what's the fastest algorithm for this problem? And there's a sort of naive brute force algorithm that runs in time roughly M to the K, or sort of more accurately about M choose K. So I'm going to hide low order terms throughout this talk. And of course, this algorithm works just by sort of enumerating all possible K-tuples and just checking for each one whether or not the given K-tuple sums to 0. And once you find one, you output it. You can actually do better than this. There's a slightly non-trivial algorithm, which is a meet in the middle algorithm, which runs in time roughly M to the K over 2. Again, I'm like hiding low order terms. People who study this problem will get annoyed with me and say I should say M to the ceiling of K over 2. The distinction is really rather important. But for the sake of this talk, I don't really care so much. So there's a meet in the middle algorithm where you sort of enumerate all possible K over 2 tuples, and then a disjoint collection of K over 2 tuples, and you merge them together somehow. And in fact, if you don't care about the constant of the exponent, which again, for my purposes, for the sake of this talk, we don't, this is actually tight. So there's a very nice lower bound due to Petrasco and Williams, showing that you can't do better than M to the order K, assuming the exponential time hypothesis, ETH. So a very well-known complexity theoretic hypothesis, which some people believe in and some don't. I think I believe in it. But actually, this isn't the only algorithm, like non-trivial algorithm that we know for this problem. There's also kind of an entirely different algorithm, or really a pair of algorithms. You can either use the finite Fourier transform, or sorry, the fast Fourier transform, or dynamic programming to get an algorithm that runs in time roughly Q. So in time roughly the size of the group. And you've probably seen something like this, at least in the context of subset sum, as opposed to K-sum. Like you probably know that in a subset sum problem, if your input values are not very large, then you can solve it faster than just enumerating. And this is the sort of analogous result in K-sum land. And again, this result is tight. So there's a lower bound, a very nice lower bound by Boot et al., quite recent, showing that if you believe SETH, then you can't do better than Q to the 1 minus epsilon. So this is quite a tight lower bound. It's even tight up to the constant and the exponent. So like what this tells us is that there are kind of two different regimes of K-sum, what I'll call the sparse regime and the dense regime. and there's kind of a phase transition between them. In the sparse regime, when m is much, much smaller than q to the 1 over k, the fastest algorithm is this mean in the middle time algorithm, and that's tight, at least up to the constant and the exponent, assuming ETH. And in the dense regime, when m is really quite large, then running an m to the k time is not the smartest idea. Instead, you should just run in q time using dynamic programming or FFT. And again, this is optimal. So, okay, it seems like we've kind of figured out this problem. There's maybe not so much to say about it anymore because this wonderful work has resolved everything. But I'm not interested in the worst case problem. I am interested in the average case problem, at least for this purposes of this talk. So what do I mean by the average case k-sum problem? Well, in this problem, it's the same problem, except now my input is uniformly random elements, A1 through AM and ZQ. Instead of arbitrary worst case elements, they're uniformly random. So this is, the most natural average case version of the problem. And the goal is exactly the same. I again want to find a k-tuple of my input elements that sums to 0 modulo q. And notice that this, at least the way I've defined it here, this problem doesn't even make sense unless m is much larger than q to the 1 over k, right? Because if m is not much larger than q to the 1 over k, then like a simple sort of union bound argument will show you that actually with high probability, there will not be a solution. So I suppose I could prove hardness for this problem, but it wouldn't be very fair. I'd be proving that it's hard to find a solution that doesn't exist. So it's not very interesting. So at least the way I've defined average case k-sum, it's only interesting in the dense regime. It's only interesting when you have a lot of samples. So again, we can think of algorithms for this problem. And of course, I showed you on the previous slide that there's a worst case algorithm that runs in time roughly q, roughly the size of the group, using FFT and dynamic programming. It's a worst case algorithm, which means it also works in the average case, of course. The average case can only be easier than the worst case. Certainly can't be any harder. And remember, in the worst case, this algorithm was actually, this upper bound was actually tight, at least assuming SETH. We can't do any better than this up to some lower order terms. So you might think that this is tight in the average case as well, but it's actually not. There's a very nice algorithm. It's a bit of a difficult algorithm to attribute to anyone because it's sort of been discovered a few different times. It's very natural. I'll show you the algorithm. So I usually call it the BKW algorithm for Bloom, Kalai, and Wasserman because that's how I first learned about it. It was also described by Wagner in a slightly different context. Some people call it the generalized birthday algorithm. But anyway, it gets this really kind of quite surprising speed up. In particular, instead of running in time q, it runs in time q to the 1 over log k. So even for a relatively small k, this is still like a significant polynomial speed up. For large k, this is kind of huge. And notice like this is like a real separation, right? Because if you believe SETH, then you have to believe that the worst case problem can't be solved in time better than q. But the average case problem provably can be solved in time q to the 1 over log k. So really quite a bit faster. So there's a real gap between the worst case and the average case here. And I should note that actually the BKW-Wagner algorithm works in a very specific regime. It works in the regime where we have so many samples m, we have q to the 1 over log k samples. Actually, it's essentially a linear time algorithm, linear in m, that only works when m is very large. And actually, this is like not so unreasonable. Often in the average case setting, really, I don't think of m as sort of a fixed parameter. Instead, I kind of imagine that my algorithm has a button that it can press, and every time it presses the button, it receives another a, and it can just press that button as many times as it wants. Of course, every time it presses the button costs 1 time step. So the BKW-Wagner algorithm presses the button many, many times, q to the 1 over log k times. It gets q to the 1 over log k samples. And once it has that many samples, it runs extremely efficiently, basically linear time. Okay. So that's the average case setting. And of course, as a complexity theorist, what I want to do here is prove that this is optimal, right? So I have an algorithm, I have an upper bound, I want to prove a lower bound. And that's in fact what we do with Zvika and Vinod. Particularly, we show that you can't do better than q to the order 1 over log k for the average case problem. The conjecture that we use is not a standard conjecture. It's not SDTH, it's not ETH. You can view this as a weakness of our work. It's a conjecture about the hardness of a certain worst case lattice problem. So what we're getting is a worst case to average case reduction, fine grained worst case to average case reduction, but it's from a problem that people typically don't study in this context. So you can view that as a weakness of our work, but it's also worth noting like the problem, which I'm not going to even bother to define. I'm not even going to tell you what a lattice is, let alone what the problem is a really well-studied problem. And it's well-studied in particular by cryptographers and up to various minor details. If you could falsify the conjecture, the hypothesis under which we show this hardness result, then you would break a bunch of crypto and a bunch of cryptographers would be annoyed with you. So modulo annoying a bunch of cryptographers, we believe this hypothesis. So non-standard but reasonable, I think is a fair way to characterize it. Okay, so before I show you our reduction, this is only a 30-minute talk. It's a simpler reduction. Let me show you the BKW Wagner algorithm, because our reduction can be viewed, at least in hindsight, as a modification of this algorithm. Also, it's really quite beautiful. And if you've never seen it before, that's a shame. You should see it. So here it is. I'm going to assume for simplicity that my parameters have a nice form. In particular, I'm going to assume that k, remember, I'm looking for a k sum. I'm going to assume that k is an integer power of 2. It's 2 to the L. And I'm going to assume that q is also, is also an Lth power. It's p to the L. And remember, BKW Wagner only works in the regime when m is much, much larger than q to the 1 over log k, which means q to the 1 over L, which means p. And you'll see where that comes up. So the idea here is I have a bunch of integers in ZQ. So I have a bunch of integers modulo Q, and Q is an Lth power. It's P to the L. So it's quite natural to write these integers in base P, right? So I can write an integer A in ZQ is A equals B0 plus B1 times P plus B2 times B squared, etc. So here these BI are just the digits or bits or whatever of A in base P. And the idea of the BKW Wagner algorithm is if I want to find a k-sum that is 0 modulo Q, it suffices to find a k-sum that's 0 modulo P and 0 modulo P squared and 0 modulo P cubed and 0 modulo P to the 4, etc. So I'm going to sort of do this iteratively. I'm going to sort of zero out the 0th digit first, and then the first digit, and then the second digit, and eventually I'll have zeroed out all the digits. So here's how the algorithm works. The first thing that I do is I try to zero out the first digit, so the first digit of your base P representation. In other words, I find many disjoint pairs I and j such that AI plus AJ is 0 modulo P. And there are a bunch of things to notice here. First of all, if M is much, much larger than P, which is my assumption, then not only will such pairs exist, but there will be many such pairs. Basically every, since my-
AI and BI the same here? Or?
I'm sorry?
Is AI and BI the same or?
So maybe my notation is slightly confusing. I guess B0 is AI mod P.
AI mod P.
Okay. Yeah, but here I guess I'm just writing things mod P and I'm forgetting about the B's. Yeah, so I'm actually not going to use the B's again. That was just kind of to explain what's going on at a high level. Does that make sense?
Yes.
Okay. Okay, cool. Sorry about that. Okay, so because my inputs are random, I expect to have many collisions. So I expect to find many AIs such that there's a J where AJ equals minus AI. In fact, I expect sort of every AI to have a friend, AJ, that equals minus AI, and I'll just collect all such pairs and group them together. So now I've sort of zeroed out the first bit or the 0th bit, if you like. The next thing I'm going to do is I'm going to look for pairs of pairs. So I'm going to look for 4 tuples I1, J1, I2, J2 that sum to 0 modulo p squared. And the way that I do this is, well, by looking at the sums of my pairs, modulo p squared, and looking for sums of pairs that sum to the negatives of each other. I think I maybe forgot to say this, but notice that I can do this in more or less linear time in M, right? Because I could just sort all the sums modulo p squared. So I can do that in like M log M time or whatever. And then I just need to check for each sum whether or not my list contains the negation of the sum. So this can be done very, very efficiently, more or less linear time. Okay, and then I just keep going. So I'm going to do this a total of L times. After the ith step, I'll have 2 to the I tuple that sums to 0 modulo p to the I. And in particular, this means that after the Lth step, I'll have a 2 to the L tuple, and 2 to the L equals K. So I'll have a K tuple that sums to 0 modulo p to the L, which is Q. So in other words, I'll have a solution to my original K-sum instance. And of course, I'm relying really heavily here on the fact that M is so large that not only do I have a K-sum modulo 2, but I also have many 2 sums modulo P, which is not guaranteed without this assumption that M is large. And I'm also relying on the assumption that my input was uniformly random so that I can expect to actually have these things. Right, and we know that that's necessary because we know that there's a lower bound in the worst case world, assuming SETH. So if this worked in the worst case, then we would violate SETH, and that would annoy some people. So we won't do that. Okay, cool. So that's the BKW Wagner algorithm. Now I'm going to use this idea to show hardness of K-sum. And of course, I need to reduce from some problem. The problem that I'm going to reduce to is a problem that's really well studied in crypto and in the lattice world that looks suspiciously like K-sum, very, very suspiciously like K-sum. It's called SIS, or short integer solutions. And the inputs to this problem, well, it's A1 through AM, sampled uniformly at random from ZQ. Now Q is a capital Q, not a lowercase q. That's the only difference. And the goal is to find x1 through xm. Oh, my notation's messed up here. It should say x1 through xm such that the sum of ai xi is 0 mod q, and the xi's have small L1 norm. So if you squint and you don't worry so much about the fact that the xi's don't necessarily need to be 0, 1, SIS is just n sum, which in some sense is really silly. I've just changed the letter k to a letter m, to the letter n. But actually, the big difference here is that like the parameters really matter. So in the K-sum world, what I'm interested in is constant k. And in the SIS world, I'm thinking of n as going to infinity. So that's the difference. I'm thinking of n as being relatively large compared to m, say comparable to m. Whereas in the K-sum world, I'm thinking of k as constant and m going to infinity. So that's the difference. And this problem in this setting is very well studied, again, in the crypto literature. In particular, we know its worst case hardness. Itai showed all the way back in 1996 that SAS, which is basically just n sum, is at least as hard as some worst case lattice problem on n-dimensional lattices. And again, I'm not going to even define this problem, but this problem is thought to be 2 to the order n hard. So we have like a very, very strong worst case to average case reduction for this problem. Actually, it turns out like this specific version of the problem is not the standard way it's written. This worst case to average case reduction was only proven much later by Jinx in 2016. But it's very similar. Okay.
Question. So the
Yes.
reason you need to take Q to be so large is so you can conjecture exponential hardness, or?
No, the reason I need to take Q to be so large, it's the same because I need there to be solutions, right? So my parameter regimes are a little different now. But this is the parameter regime that I need in order for there to be, wait, okay, sorry, I'm confused, 1 sec. No, yes, exactly what you said was right. I need Q to be large for hardness. Sorry, yes.
And I think there was a question asked. I don't know if you can see it. I cannot see it here in the Zoom box.
I think I can see it on my iPad. Does your parameter regime imply a solution always exists and thus a lower bound under ETH is unlikely? Yes, my parameter regime, I guess that a solution not always exists, but almost always exists with high probability. And therefore, yes. So like one way of thinking about what's going on here is kind of I'm doing complexity in like the TFNP world where solutions are likely. It's not exactly TFNP, of course, because it's an average case problem and I only have a solution with high probability. But yeah, I don't expect to see like ETH or SETH hardness here, partially because you don't expect to reduce a 3-sat or whatever to a total problem. And this is more or less a total problem. I hope that answers your question. Cool. Okay, more questions? This is wonderful. Okay, so our goal here is going to be to reduce SIS, which is an average case n sum, to k sum. And to get the parameters right, remember I want q to the 1 over log k hardness. I know that SIS is 2 to the order n hard under a reasonable conjecture. So I want 2 to the n to be like q to the 1 over log k in order to make this go through. Okay. So let me just remind you of the BKW-Wagner algorithm because our reduction is very similar to the BKW-Wagner algorithm. And I want to point out that you can view the BKW-Wagner algorithm as kind of, sort of, almost a reduction. What it's reducing is it's a reduction from k-sum with modulus q to 2-sum with modulus p. It's not exactly a reduction because it's like not black box, but that's basically what it's doing, right? At every one of these steps, I'm solving a bunch of 2-sum instances, mod p, and I'm using those solutions to solve k-sum modulo q. Okay, so here's an idea of a reduction that doesn't quite work, and then I'll explain how to fix it. So the idea, just like for BKW, I'm going to choose my parameters conveniently. In fact, I can get away with this because I know hardness for SIS for a wide range of parameters. So I'm going to take n to be k to the L. So it's the Lth power of k for some L. And I'm going to take big Q to be little q to the L. This is very similar to what I did with Wagner, with BKW Wagner. And I'm going to use my k-sum oracle to find m over k disjoint k tuples that sum to 0 modulo little q. So this is, again, very similar to the BKW strategy. And then I'm going to use my k-sum oracle again to find disjoint k squared tuples that sum to 0 modulo q squared, etc. And after doing this L times, I'm going to find an n tuple, a k to the L, which is an n tuple, that sums to 0 modulo big Q, which is little q to the L. So it's the same idea, except I've plugged in, instead of using 2, I'm using k and little q. And I'm using a k-sum oracle instead of solving 2-sum instances. So this almost works, comes really close to working. The only issue is that it doesn't give an average case. It doesn't give an average case to average case reduction. So let's think about this for a second. Let's think about like the distribution, like how I would actually do step 1. So for step 1, I don't just need to find a single k tuple that sums to 0 mod q. I need to find many, many k tuples that sum to 0 mod q. Yeah. And the most obvious way to do so would be to just call, well, the laziest way to do so would be to call my k-sum oracle on the same input over and over and over again. And that's, in some sense, not bad because by definition, my input comes from an SIS instance. It is, in fact, uniformly random. So it is an average case instance. But of course, if I call my k-sum oracle on the same input over and over and over again, it's just going to give me the same answer every time. So that's no good. So the next thing you could imagine doing is call my k-sum oracle on the first m, on all m elements, and then call it on m minus k elements, where I've taken out the k elements from whatever k tuple it gives me the first time. And then I call it an m minus 2k elements and m minus 3k elements, etc. And I do that roughly m over k times. to get roughly M over K disjoint K tuples. So this idea would work if we had a worst case K-sum oracle. The problem is that if I try to do this with an average case K-sum oracle, it can misbehave. In particular, I think it's helpful to imagine that our K-sum oracle has some preferences. For example, suppose our K-sum oracle only likes to output K-sums that tend to have even integers in them, right? So if we had such an oracle and it tends to find K-tuples with even integers, after I run it a bunch of times, it's going to, the instances that I'm going to start calling it on are going to be depleted of even integers. And it's going to complain. It's going to say, that's no good. That's not an average case instance. I like even integers. There are no even integers here. And it's going to refuse to cooperate. So this does work for a worst case K-sum oracle. And it does, in fact, give, if you plug in all the parameters, which I'm not going to bother to do, q to the 1 over log k hardness for worst case K-sum. But that's not interesting, right? Because we already know q to the 1 minus epsilon hardness for worst case K-sum. So we get a worse result, and it's not particularly interesting. It does not work for average case hardness. And now let me just sort of sketch briefly the main technical step in the paper, which is we convert little m samples, A1 through AM, into big M samples, A1 prime through AM prime, where each of the AI primes is the sum of a random K tuple of the AIs. And the idea here is that I can take many, many such K tuples, and I can sort of blow up my number of samples, then run this algorithm on completely disjoint sets, sort of collapse down the number of samples that I have, and then blow up again, collapse down, blow up again, collapse down. And it turns out that this works, that the AI primes will be statistically close to independent uniform samples. And if I get K sums of the AI primes, this gives me K squared sums of the AI. Anyway, this is the most technical part of our work. It takes some work to go through, but I think the high level idea for this audience and for this talk is more interesting than the details. So let me just summarize what's going on. So we have so before this work, we had essentially tight bounds for the worst case K-sum. There's this sort of transition that happens between the sparse and dense regime. And we show more or less tight lower bound for average case K-sum in the dense regime. And we do so using non-standard worst case fine grained hardness assumption, which is the hardness of a certain lattice problem. And I just want to leave you with an open question, which is more of like a future direction or a challenge or something, which is, I feel like K-sum is a problem that people really care about in fine grained complexity. And so now we have this fact: average case K-sum is hard in the dense regime under a reasonable worst case assumption. So the obvious next step to me seems to be, what can we reduce K-sum to? In other words, what other average case fine grained hardness results can we prove given this result? So thanks. I think I ran slightly over time, so I apologize for that, but that's it.
We started a bit late too, so let's thank Noah.
Thank you.
Are there any questions from the audience or from the online audience? So
Benny has a very nice
question. Has a question, so maybe you can read it out.
Yeah, so Benny asked if he said that I show that BKW is tight in this particular context, and he's wondering if I can use that to conclude that BKW is tight in the LPN regime. So Benny's basically asking about modulus Q equals 2. So I didn't say very much about what restrictions on the modulus I need. It turns out that I can't handle arbitrarily small moduli. I can handle constant modulus, but not arbitrarily small constant modulus. So in particular, I do not know how to prove such results for Q equals 2 for the LPN regime. I think that would be pretty exciting. And I don't know that there's a fundamental barrier. I just know that like our particular techniques don't work there. We did try.
So is there a direct connection between LPN and subset sum? Because in LPN you have also some noise, or that's
yeah. I suspect like so SIS, the problem that I showed, is closely related to LWE. And just like SIS is related to LWE, LPN is related to some average case short coding problem. And so I suspect when Benny said LPN, what he really meant was, I think it's sometimes called binary SVP, which is a kind of variant of SIS in the Q equals 2 world. So I think yeah, there's I don't think there's a very good name for it, which is probably why Benny said LPN.
Okay. Any more questions from either the physical or the virtual audience? Thanks. Let's thank Noah again then for a very nice talk. And we'll pick up in about 25 minutes. So meet back here at 11. Thanks.
Cool. Thanks, everyone.